So I probably told everybody as they were walking in, but I'm Nick. I organize meetups, emails, and all that stuff for me. So today we're going to hear about Cassandra Umbel from Travis. Next month is actually already on the schedule. We're going to do a talk on Cassandra and Spark. So we'll have Matt File, co-founder of DataStax. He's going to do a little high-level intro, and then I'll do kind of the more technical side of that. That's October 18th. So I'll probably send out an email about that tomorrow, but put that on your calendars. In other Cassandra news, anybody make it to the summit in California? I think I saw any of these faces there. But if you didn't know, the Cassandra Summit was last week. Went great. 5,800 people or so there. Lots of awesome talks. A lot of slides are already online, but we're waiting for videos to get processed and all that stuff. And then videos and slides on Planet Cassandra. If you watch that, you'll see a post go up about all that stuff. So keep an eye out about that. There's lots of awesome talks from Apple, Netflix, Sony, bunches of smaller startups, a lot of good stuff. So keep an eye out for that. Any organizational questions? People hiring Cassandra developers, anything like that? All right. Well, here's Travis. He's going to tell us about Cassandra Umbel.
Thanks, guys. Thanks for coming out. All right, let me try to stay out of the way. So I'm Travis Turner. I'm the Chief Data Scientist and co-founder at Umbel. We are a startup here in Austin that we founded in 2010. So we've been around about 4 years. And this is Umbel's blurb, but we empower companies to convert people-based data into addressable action and actionable relationships. And I think the core thing to take out of that is that Umbel's people-based. All the data and the metrics that we are interested in are around our clients, users, and the people who engage with those clients. A lot of our clients are in media and entertainment. We have a lot of like sports teams and things like that. So it's typically clients who have a fairly engaged user base that that our clients are interested in, maintaining that engagement, growing that engagement, knowing more about those people and things like that. So tonight I'll talk about 3 things. One of the core things in our product is being able to segment audiences. Segmentation of this people-based data is really important. And I mean, that's nothing new, sort of, from standard things like you're interested in, the males from California in your audience and what that looks like. So, demographic segmentation and things like that. But we also get into behavioral segmentation and sort of brand affinity segmentation. Just any way that we can slice this data is interesting to us because we can use those segments to drive the other parts of our platform. So the second thing I'm going to talk about is a product called Pilosa, which is a product that we developed in-house. We developed it in Go. And so I'm going to spend a bit of time talking about that, which isn't necessarily about Cassandra, but we use Cassandra as a back-end persistent data store for that product. So I'll talk a little bit about that. So that's a third one, is sort of the persistent storage we use on the back end for that product. So at a high level, this is just to give you an idea of kind of the flow of data through Umbel and how we make it useful. Most of our data starts from various SDKs like JavaScript SDKs, Android. We have an Android SDK and iOS SDK that our clients will install into their website or their mobile application. And those SDKs will send us events. It's similar to the way Google Analytics works, where you're constantly sending events about whatever actions or whatever information that the client gets to send to us. And then the last option is some of our clients send us data server side directly to our API, so it doesn't go through any kind of SDK. But so we get this, just flood of data, flood of events and information in, and they're really just raw events. And from there, they kind of go into three places. The first place is they're sort of pushed off, flushed out to S3, just kind of as backup in its raw format. So everything that comes through our system goes out to S3. A lot of it, the data also goes into a Hadoop cluster that we have that we're doing a lot of sort of our data analysis around, and I'm not going to talk about that so much today, but that's part of what we do with that data that goes into Hadoop. We look into things like our customers who are sending us transactional data, like the e-commerce sites, will do lifetime value analysis and things, long looking at the lifespan of a customer and what that means. We also do a lot of similarity calculations, like looking for types of audiences who might be similar to the ones that clients may be interested in. So, if you're a sports team and you have you have this group of people who tend to buy VIP passes, we can take that audience and sort of build basically build a model of what that audience looks like, and then go out and look for similar audiences, because that we want to find more people who are likely to buy VIP passes to the sports games, for example. And then the sort of main real-time flow of data goes through this RabbitMQ, and we've got Celery workers that are taking these events that are coming through our capture system and doing kind of work on those and determining what to do with them. And right now, the main goal is to build a profile out of that data. So we determine, what's the common user, and we start to receive attributes around that. So we might, whether it's anonymous or not, we might build a profile of an anonymous user and then start to see the patterns of their activity on a certain client's website. And we start to add those attributes to that profile, and that gets stored in Cassandra. And I'll go through that a little bit more later. And then we were using Elasticsearch to allow us to do sort of real-time queries and against this data. And I might as well just show you some examples. So this is an example of one of the reports that we generate from our product. This is like a profile sheet. One of our clients is SB Nation. It's a big sports blog. So I don't know if you can see the numbers, but that one's really heavily male. But so we have general demographic data around their audience. We have the top 30 brand affinities that that audience likes. We have geographical data and things like that. So your typical sort of metrics around an audience. And then to take that, the next step is we can drill into any one of those within that audience, drill into any segment and create this same sort of profile sheet. So within the SB Nation audience, I've drilled into the people who have some sort of affinity for Dos Equis. Now, what does that audience look like, and how are their brand affinities different? And so this, we were doing this with Elasticsearch, and this is not so terribly difficult. I mean, we get a ton of data, so it becomes difficult at a large scale. But some of the things that were starting to become challenging were, maintaining this kind of these top-end queries on an ad hoc segment of, tens of millions of different attributes that somebody might possibly decide on. And so we started to think about how we might continue to be able to do that without some of the pain that we were having with Elasticsearch. We were growing Elasticsearch, our cluster was getting really big. It's, for it to be effective and for these ad hoc queries to work well, a lot of that data is retained in memory. And if it's, having to pull off a disk, all of a sudden, what maybe a 1 second, page load for a complicated report turns into a 20-second page load, and that was, that's not acceptable. So Pilosa is our solution to being able to segment this audience in a really fast way, keeping it in memory. And so I'll go through that. Yeah, so here was our stack, and this is what we changed, and this is what I'm going to talk about. So swapping out Elasticsearch for Pilosa, and that logo is something silly somebody made at our office. But and then also how Pilosa uses Cassandra as a persistent backend store. So I'm going to go through some basic kind of how it works at a really high level, just so I can talk about it. This might be a little oversimplified. But the idea is that within our system, everything's people-based. So, we build everything around this profile of a person, and then around that are attributes, and they can be signals about a brand. They can be demographics, like male or the state that they live in or anything like that, or they can be behavioral events, like that they, like I said before, they purchased a ticket, or they watched a video on a website, or just whatever it is. It's completely up to the client. So just these behavioral events that just continually get associated to this profile. And so to start thinking about it, the way we've designed Pilosa, we have these people, and start mapping it out and thinking of it as a large map of these profiles along the top, and then every column represents a person and every attribute that's associated with them. I did a lot of brand attributes just because it's kind of easier to visualize, but they could be anything. And so let's see. Oops. Yeah. Okay. So getting closer to the bitmap indexing, if you think of that map that we had of all the brands associated with the person, and turn it into a map of ones and zeros, then that's kind of what we're wanting. And what that lets us do is start to perform, bitwise operations on it. So for example, ultimately I want to be able to say, give me this segment of my audience that has some signal about Family Guy and Star Wars. I want to know who those people are. And so at a really high level, it's very simplified. I can do that, and I see, those 5 people make up the segment of my audience that has those 2 affinities. Same thing with ors, just a different result, Family Guy or Star Wars. And then, I also want to be able to exclude some things. So I want to know all the people who like Family Guy or Star Wars, and maybe they haven't signed up for the newsletter on my website. And that's a completely different segment of the audience, but that's what I'm interested in getting to. So from here, we start to imagine a sort of infinite grid of profiles along the top and a vertical list of attributes that ideally go on forever. And so our goal is that we're going to be able to do this, and we can do it fast, which means we want to do this in memory. And as it gets bigger and bigger, we want it to be distributed across servers and across nodes, and let it grow as much as it needs to. So in order to do that, we start thinking about breaking it up, because ultimately it's going to need to be distributed. So we think of each one of these blocks as being managed by a certain process, or a certain node on a server. And yeah, I guess that's what this shows, is that no matter where in this grid this block is, that information that pertains to that is going to be associated to some process somewhere, so that we can spread this load out and do this quickly. So we break it up into manageable pieces. And we did, when we're building Pilosa, we did set some boundaries. We put a limit of 2 to the 64th on here, which is huge. We don't ever get anywhere near that, obviously, because that's like 18 billion or something. But it was just a decision that we made as we were architecting it. So we're going to say our map space isn't going to get any wider than that, but maybe it can get as long as it needs to. And so to continue down, I'll just kind of describe how we sort of break this up and assign this data out to different processes. The first thing we do is we define these vertical slices of the data. Each slice is 2 to the 16th bits, 64K bits wide. So every slice represents 65,000 possible profiles. The next thing that we start thinking about is breaking out each one of these chunks, and we call these fragments. And the fragment is the largest piece of data that will reside together in the system. So that fragment will be managed by a single process, and everything within that fragment will be in the same memory space. Any other fragment might be on a completely different server, or might be on the same server, a different process, or whatever. Okay, so now if we think about these, this 64 kilobits and start breaking that down, we break it down again into 32 what we call chunks of 2048 bits each. And we break that down again into another 32, so let me keep going, what we call blocks of 64 bits. So what we eventually end up with is a 64-bit integer position that can represent that one little piece of this potentially massively wide bitmap. And our goal is, the assumption is we're going to have sort of potentially sparse bitmaps. We don't want to, if I stored, if I had 2 million profiles in this space and I just stored the whole bitmap uncompressed, it's going to be 2 megs. But if I just start storing only portions of the data that are interesting to me, or that, in other words, that have at least 1 bit set, and I've broken it down to, I'm willing to make the smallest piece of data I saved is 64 bits. So if I just had a completely blank slate and I set 1 bit, I'm going to end up setting a 64-bit integer with 63 zeros and 1 bit set in it. Does that make sense? Yeah, so I'll go through an example. So one of the things that when we're doing, for example, on the right, when we're doing a set bit, we need to know ultimately which block is going to be responsible for that profile ID. And so if we say the profile ID, which would be the column 150,000, so the 150,000th profile, what we do is we get the binary version of that. And the first thing is you divide by 16, which is really, shifting the bits out 16, the least significant bits out, and you're left with this 2. And so what that gives you is your slice, a map to a slice. And that makes sense because the first 2 slices would represent 130,000 profiles. So 150,000 can be somewhere in that slice 2, and it's 0 indexed. So so then the next thing we do, we take that least significant data, that's the 16 bits. So this is basically the modulus of our 150,000 and 2 to the 16th. And we do another bit shifting by 11, which is the 2048 that you see in this chunk. And that leaves the 01001, which is 9. So within this green space, it's in the 9th chunk. Again, we take that modulus of the original number, shift out another 6 bits, and we find this. It's in the 7th block of this chunk. And then what we're left over with is that modulus is 48. So the value that's going to go in there is not 48, but 2 to the 48th, because we're just setting that 1 bit. So the value that we would see in that block 7 would be 2 to the 48th. I don't know what that is, but it's some big number. Does that kind of make sense, how we're doing that? And why? Okay, so Cassandra has persistent storage. So we developed Pilosa to be able to run completely in memory, so you don't have to have a backend storage, but you can plug in different backends. We've only written a couple, like LevelDB and Cassandra, and then we also have a in-memory backend storage, which doesn't make sense, but just for testing, it's useful. And so this is a sort of the CQL of the create of the backend storage in Cassandra. So we have the bitmap ID of a database, So this bitmap space, we can have, you know, as many of those as we want, just name them as a different database. Frame, I'll talk about in a little while. Slice we talked about. It's that vertical portion of the bitmap, and then the chunk key in the index, and then the block is the actual value. So that's where that 64-bit integer gets stored. And then the primary key is, well, that's clear. Bitmap, DB, frame, and slice are what we key on, and then our column keys are the chunk key and the block index. So that lets us pull up all the values pertaining to a specific bitmap within the same row. Yeah, so using my example, this is with a completely empty data set. If I ran up in the top left the PQL statement to set bitmap 88 frame, the second two parameters I'll go over in a minute, but then profile 150,000 was the example we did. This is what ends up in Cassandra. So our bitmap was 88, the DB I put was test, frame is D, slice was 2, chunk key was 9, block index was 7, and the block is, this is 2 to the 48th. And then the one that has chunk key -1 is actually, we use that as a sum, a total, so it represents how many bits are set for that bitmap within that chunk. So right now it's just 1 because I just set the 1. Okay. All right, so I talked about, let me go back here. So I haven't talked about this frame yet, this frame column. And I'll go over how we use that, because it's I mean, it's nice to have this big just map of generic bitmaps, but we needed a little more usefulness out of it. So we have this with our slices, and so the idea of a frame is to take a group of bitmaps and sort of contain them together and say that we're going to keep them in a certain container, and we might perform different actions on them just because they're in this frame. So right now we've got 3 different types. This is the default type, which means it just gets put in to the frame. There's no order and there's no logic around it knowing. Nothing useful is done with it other than it's just stored in there. We have another type that's time-based that I'll go over, and then we have a top-in. So I'll go through each of those. So the default is kind of what we already went through. So I set bitmap 88, frame foo for profile 150,000. It just means I'm going to set that bit, and that's it. The time-based one's a little different. A lot of the types of queries that we need to do are more than just, one-time set. So, for instance, if you're male, for example, that one's probably going to stay set, and there's no really time that needs to go with that. But if it's maybe that you made a purchase on the website, I want to be able to mark that every time that happens, So I don't want just this generic bitmap that represents that I made a purchase on a website, and once that bit's set, it's just always set. That doesn't help me. So we introduced the ability to pass in time with that, and it still goes in as a single set. So, but it takes a date time parameter. And internally what it does, so right at the top is my set where I'm setting, bitmap 88 again. I'm putting it in this frame that I called bar.t. Still profile ID 150,000, but I gave it a timestamp. And internally what that does is it passes that bitmap ID 88 and that timestamp through a function that breaks it out into, this is configurable, but into different parts of the date time. So the way we have it configured, we're only interested in granularity down to hours. So it would create 4 bitmap IDs that are based on bitmap 88 and the time. And when we were developing this, we thought about a lot of ways of keeping our bitmap IDs 64-bit and having another value that represented time or something like that. But it made more sense for what we're doing to sort of cram both of those pieces of information into the same 64-bit space. So we gave up 20 bits to represent our time date. And this is configurable. This is how we use it at Umbel. So we can represent 60 years with the hours down to hour granularity in 20 bits. And we just start at 2010. So basically we have a window of 60 years that we can track. And really that's more than we need. And then that leaves us still with a 44-bit bitmap ID, which is more than we ever run into. But that allowed us to keep our bitmap ID still as a 64-bit integer, and we didn't have to re-architect a lot of the software on the back end. But so what happens on these time-based sets is that I effectively set 4 bits every time I do a time-based one, and it gives me 4 distinct bitmap IDs. What's interesting about that is that on the get, I can pass in a time range. So in this case, I said from August 1st to September 4th at 3 a.m. And internally what that does is it calculates the minimum, the least amount of bitmaps that can represent that time window. And in this case, there's 7 of them. I needed to get the month of August, and then three days of September, and then the first 3 hours of the 4th day of September, and union those together. And what I'm left with is a representation of the segment of people who had that event 88 between that time window.
So basically you broke up the date time into, and then you were treating them as attributes.
Yeah, exactly. Yeah. Yeah, it's similar to the way, I guess you would do sort of a low cardinality index, maybe,
So like Elasticsearch tri-field.
Yeah. Yeah. And then the last frame type we have right now is top in. And what that does is it keeps the bitmaps within the frame sorted by, currently the way we use it is it's sorted by the number of bits set. So the one with the most bits set within that bitmap floats to the top. And what we had to do for that is impose a limit, and that's configurable, but we do about 50,000. So we'll keep a 50,000 bitmap sorted by that count. Another limitation is that we can only represent, we can only allow one fragment. So, you know, each of these fragments, there's 4 in this picture, you know, will be managed by a different process, but I can't have, you know, any more vertical ones like that. That one fragment is 50,000 bitmaps tall, and it never gets bigger than that. It doesn't grow. So that's one of the limitations of this sorting one. And then another thing that it does is as bits are set and as they float up, as new bitmaps are created and they start to float up and our numbers get over 50,000, those the ones that are falling below 50,000 get pulled out of memory, so that we basically stay around 50,000. But another thing we do is if a bit's set into this frame and there's no, that bitmap isn't represented in the frame because maybe it's less than 50,000 or maybe it's new, that set still gets queued and goes out to Cassandra. And what will happen is whenever it hits Cassandra, it'll look for that counter that was stored in Cassandra and say, you know, what is this count? Is it enough to get me back into the list of 50,000? If it is, it'll pull it back in there and maybe ship something else out. And there's a lot of work that goes around. You know, we don't do that on every single set bit. You know, there's queuing and sort of things that make that happen periodically, not as opposed to on every set. Oh, right. So, yeah, so if you remember, when I had set that bit, I had this chunk key of -1 with my counter of 1. So if I had set 88 and it wasn't in there and I came here, I could look in this this -1 row and see that, you know, there's 1 in there. I'm setting it to 2, you know, or maybe there's 100 in there, and so maybe now that I made it 101, that's enough to get it back out to the main list. So what that lets us do is we can start to do top-in queries, and this is an example of the syntax of a top-in query, and where basically I'm saying, where it says get 222, I'm saying go get the bitmap 222 out of the foo frame, which is somewhere else in the system, and I want to use that segment of people. And you know, that could be anything. That get 22 could also be one of our Family Guy and Star Wars, and not, you know, and so it's whatever this you know, representation of a segment of people is, and do a top in on that against this brand ends frame. So what you're saying is, like, given this segment of people that I've just ad hoc built a query for, return the top in of information out of this frame. And so in this example, we use it to store popular brands, and this is from PGA. PGA is one of our clients, so this is from a golf audience, obviously. But so you know, you start to get Tiger Woods and PGA and all that stuff kind of floated to the top. Yeah. And I guess I can go through like some demos a little bit. I know I didn't cover a whole lot of Cassandra stuff necessarily, but maybe if you guys have questions, or if there's something I could, you guys have any questions about what I've gone over so far?
Can you describe in more detail how you do that top end? What system is processing that? I mean, you said it was done in a queuing. Did I hear that? Or like what manages that? Is that something that?
It's managed by the Pilosa process itself. So just like the rest of the fragments of data within Pilosa, there's a process that's managing this block of data, and it's it knows about its complete space. It knows all the bitmaps that are in it. It knows its counts of bitmaps, and so it can internally keep those sorted.
In memory.
Yeah, in memory. Yeah.
How big is this Pilosa database?
Right now, I mean, it just depends, but we're running like 32 processes, and we've tested on, we actually can have one process manage multiple fragments, and we have like 100 fragments per process on those 32 processes, so like maybe 3,200 fragments. I'm trying to think, I wish I'd brought some better numbers, but like our Elasticsearch data and memory was, not huge, but like 200 gigs or something on one of our systems, and mapped directly in here it was, like 16 or something. It's significantly lighter, and we've obviously stripped out like all functionality, of anything like Elasticsearch. There's no faceting or anything like that. Like our goal was basically to be able to segment fast in memory. And so, we've added a little bit of the sort of sorting functionality on top of it, but in general, it's not big. One thing I can talk about. One thing I didn't talk about is growing vertically. So we actually use if you have this slice of data and you want to just continually add fragments and let it grow vertically forever, when you send Pilosa bitmap ID, it has to know where to send that, which fragment's responsible for that bitmap ID. We tell it which database, and we tell it which frame, and based on the query, usually if it's a set bit, it'll know which slice. Because if you know the profile ID, you know which slice it's going to go into. But then within this slice, it uses a consistent hash ring to determine which fragment it's going to go to, and that so then that value in the consistent hash ring sends it to the correct process that's managing that fragment of data. And I didn't talk about that very much, but
So it's a single thread per fragment?
yeah. And there's there's definitely a lot more that we'll test on, how a lot of it depends on how sparse your data is within there. If it ends up being pretty sparse, there's not a lot of memory being used for that fragment, but it just really depends on your data. So we're still toying around and playing around with what works and trying to figure out what's the best balance for us.
Did you consider any other store besides Cassandra, and what made you favor Cassandra?
Well, mainly, No, I mean, originally we wrote it without a backend, but realized that was, let me go back to this oh wait. Previously when we had Elasticsearch here, if we lost, for some reason, if Elasticsearch went down or if we lost an index or something and we needed to rebuild that, we'd end up having to queue up some jobs and that would go, sort of pull that data out of Cassandra again and kind of roll back through this process and build that index, and it took a long time. So what was nice about this is that with the way that Pilosa works, it will actually look for the bitmap within its own memory space if it knows it's responsible for it. And if it doesn't find it, then it'll go out and look and hit Cassandra. So you can completely shut down Pilosa and start it up. It'll be completely empty and start querying it, and it'll return queries. But it's a little slower because it's sort of warming it from Cassandra. We do have some processes that, if that happens, we'll try to warm it with the most useful data, especially in the brands one that's sorted. That's kind of the most important. But to answer your question, we use Cassandra primarily because it fit well with the way the columnar storage worked. We could keep those bitmaps all in the same column. It was nice. And we were already using it for, just really comfortable with it. So, yeah, we didn't necessarily consider any other backend.
How large is your Cassandra ring? How many nodes do you say?
I think right now it's like 18, and we're in AWS, so and that's not all for Pilosa. That's we use it for we use it for a lot of our just normal storage, but those are on extra larges, and I think there's like 1.7 terabytes per server. Not that they're completely full, but yeah, that's what our current cluster is. Yeah, the Pilosa one's actually really small. I mean, there's not. It's really. It doesn't take much to store a ton of integers. But.
Do you do a write for every modification, or do you queue up a bunch of them and then flush periodically?
Yeah, that's a good question. We do. It will do that. It will start to queue them up if it has to, but in general, we try to. It definitely writes it in memory right away. But the flush out to Cassandra, there is some intelligence around it knowing if it has the bandwidth to, within the process to do that, or if it needs to wait a little bit. The good thing is that because that one process is managing that memory space, you don't really ever get in trouble. I mean, I guess if you hadn't written out to Cassandra and you lost that Pilosa node, the data that you brought back in after you started it back up would be behind or would be old. And in that case, we'd have to do what we're doing now with Elasticsearch and sort of refresh the index from our main storage of data, which takes a lot longer, but we could, kind of update the numbers and make sure they're correct.
Are you guys in multiple data centers or anything like that, or are you just running in one region, EC2? Or?
Yeah, we're in one region. We're in multiple ECs. Yeah, but yeah, it's definitely that's definitely something that we're moving to. Multi-region, but we haven't done it. We did it briefly early on, but being a startup with the we didn't use it as much as we needed to, so we shut that one down.
Does Pilosa have replicas, and does it follow like master-slave replication kind of thing, just like a master shard and memory shard?
That's a good question. Yeah, there's so among the nodes, there's no master, like just not considering replication, but just considering the cluster itself. There's no master, so you can send a query to any node, and it each node has a query engine that will build a query plan and determine which servers or which processes are responsible for the data that you're asking for, and then send that query plan out and wait for the response. So there's no master there. As far as replication, there is a configurable way to associate a fragment to multiple processes. So we'll actually, you could, write the same bit out to 3 different processes. We haven't spent a lot of time on necessarily what happens when one of those fails, which, I mean, if it fails, it just won't be read from, but if they get out of sync somehow. So we haven't spent as much time, we will, but we haven't spent that much time with it just because in general, it's an index, so it's not the canonical data. We can always refresh it from our primary data store.
Do you guys use anything for the coordination of the processes, or is it kind of just static, and so there's no coordination needed?
We use etcd. I don't know if you guys are familiar with it. It's written in Go too. And so it's sort of a layer that manages the processes and the fragments and their locations, and so that's how when you write a query to one node, it knows the information about the other nodes. We also auto allocate fragments. So if I set a bit to some slice that has never had a bit in it before, we'll auto allocate that memory space and assign it to an available process. So there's some logic in there around what processes are available and how many additional fragments they can handle.
How long has Pilosa been live in production?
Live in production? Not that long, so maybe less than 6 months. We've been working on it for a little over a year. Yeah, so it's relatively new.
Any interesting considerations using Go, and I guess presumably use Go SQL or something to interact with the standard?
Yeah. That's the. I don't know if there's any interesting there. I mean, we did do the the prepared statements, I guess. I didn't ever test on how much difference that made, but yeah. Most of our Cassandra, the interface with Cassandra is pretty basic in this tool.
Do you ever try and detect if an index gets out of date? Like, is there a way of flagging it? Like you said, I guess you're flushing these indexes to Cassandra. Mm-hmm. Is there ever a detection like, oh, we missed something with this particular one, we need to refresh it from primary data? Mm-hmm. Or does that just, you prevent it from happening to begin with and assume it never happens?
Yeah, like if it didn't get set initially, Sorry, tell me.
Yeah, so I mean, you mentioned how sometimes you had three Pilosa nodes receive something, and if one of them was out of date and wrote to it out of date information, out of order information.
Wrote to Cassandra out of order?
Wrote to Cassandra, yeah, out of order.
I see.
Because I can imagine if you have three of them, you have a race condition about who gets there first. And one of them slows down, it writes.
Yeah, so we don't have all three of them writing to Cassandra the same information. Yeah, yeah, that part's tricky, but there's logic in there that makes sure that only one of them is doing that out to Cassandra.
So you have like an election process?
Yeah.
Okay.
Yeah. That's a good question.